Welcome to Daily Podcast, The Future of Intelligence. Reinforcement learning, right? It's like, teaching a computer to play a game, yeah?
Exactly. Except the game could be anything. Managing energy resources, controlling a robot, even, just navigating a complex environment.
So, it's about learning through trial and error, basically?
Yeah, but smarter trial and error. It's not just random. The agent learns which actions lead to the biggest rewards over time. It's all about maximizing that cumulative reward. Fascinating stuff.
So, how is it different from, say, supervised learning? I mean, they both involve learning, right?
Right, but in supervised learning, you give the computer labeled data, like showing it pictures of cats and telling it, this is a cat. Reinforcement learning? No labels. The agent figures things out on its own through interacting with its environment.
Oh? So, like a child learning to walk? They don't have explicit instructions, they just try things, fall down, get up, right? Eventually, they get it.
Precisely. And that whole process of, balancing exploration, trying new things, with exploitation, using what it's already learned, that's key. It's that exploration-exploitation dilemma. Tricky stuff.
I see, interesting. So, tell me more about this Markov decision process, or MDP. It seems pretty central to this whole thing.
Absolutely. It's the framework that defines the reinforcement learning problem. You have states, which describe the current situation, actions the agent can take, and rewards for those actions, which can be positive or, negative.
And, the transition probabilities? What are those, exactly?
Those define how likely it is to move from one state to another after taking a particular action. It's like, if I'm in this state and I do this action, what's the chance I'll end up in that state? It gets complex quickly, especially in large environments.
Got it. Now, the Wikipedia article mentioned dynamic programming. How does that fit in?
Many reinforcement learning algorithms use dynamic programming techniques. But, unlike classical dynamic programming, reinforcement learning doesn't need a perfect model of the environment. That's a huge advantage.
So, it can handle situations where we don't know everything about how the world works? That's pretty powerful.
Exactly. And, it's used in so many fields: game theory, control theory, operations research, the list goes on.
So, it's not just about playing games then? It has real-world applications?
Oh, absolutely. Think self-driving cars, optimizing energy grids, personalized medicine. It's really changing the game in a lot of areas. It's the future, really.
So, we were talking about how powerful reinforcement learning is, and it's because it uses samples to optimize performance, right? And, function approximation for large environments?
Yeah, exactly. Those two things are key. It means RL can tackle huge, complex environments where, maybe we don't have all the answers up front.
So, like, even if we do have a model of the environment, RL can still be useful if there's no easy analytical solution?
Right. Or if we only have a simulation. Or even better, when we just have to interact with the environment directly to learn anything about it. That's where it gets really interesting.
It's turning planning problems into learning problems, essentially?
Precisely. Now, one crucial aspect is exploration. This exploration versus exploitation dilemma, it's a classic. How much do you try new things versus stick with what you know works, right?
Yeah, like the multi-armed bandit problem, I've heard of that. Or finite state space Markov decision processes?
Exactly. It's been studied extensively in those contexts. And you need clever exploration, because just picking actions randomly? Not very effective.
So, epsilon greedy is one approach, where epsilon controls how much you explore.
Yeah, it's a simple but surprisingly effective method. Epsilon can be fixed, or it can change over time, based on a schedule or some heuristics.
Okay, so even if we figure out the exploration bit, there's still the challenge of using past experience to learn which actions lead to better rewards. Right?
Absolutely. And that brings us to the criterion of optimality, and the concept of a policy. It's how the agent chooses its actions, basically.
The policy maps the current state to the probability of taking each action. So, there are deterministic policies too, I guess. Where it just picks one action for each state.
Right. Now, the state value function, vpi, tells us how good it is to be in a particular state, in terms of expected future rewards.
So, if vpi is high for a state, that means being in that state is likely to lead to good things down the line, right?
Exactly. And the goal is to find a policy that maximizes this expected discounted return. The discounted part means rewards further in the future are worth less than immediate rewards.
Makes sense. So, a brute force approach would be to try every possible policy and see which one gets the best return. But that's usually not feasible.
Yeah, too many policies, too much variance in the returns. So, we need smarter ways. Value function estimation and direct policy search are two main approaches.
So, we left off talking about finding the optimal policy, right? And how a brute force approach is usually out of the question.
Yeah, way too complex. So, we need smarter strategies. Like, value function estimation or direct policy search. Those are the big two.
Okay, so value function estimation, that's about figuring out how good it is to be in a given state, right? In terms of future rewards?
Exactly. And then you can use that information to guide your policy. Like, always choose the action that leads to the state with the highest value.
Sounds reasonable. But how do you actually estimate these value functions?
Well, there's Monte Carlo methods, for one. They're all about learning from experience, Just interacting with the environment.
Oh? So, you don't need to know all the transition probabilities and stuff?
Nope. Just run a bunch of episodes, see what rewards you get, and average them out. It's surprisingly effective.
So, if you get a big reward after taking a certain action in a certain state, you update the value of that state action pair, right?
Exactly. But, there's a catch. These Monte Carlo methods only work for episodic tasks. Things that have a definite end.
I see. What about tasks that just go on forever?
Then you might want to look at temporal difference methods, or TD methods for short. These are pretty clever.
How so?
Well, they can learn from incomplete episodes. They don't have to wait until the end to update their estimates.
Oh, that's handy. So they're kind of like a combination of dynamic programming and Monte Carlo, right? They use the Bellman equation, but they also learn from samples.
You got it. And there's this parameter, lambda, that lets you control how much you rely on the Bellman equation versus the actual samples.
So, you can tune it to get the best of both worlds?
Exactly. Now, one tricky thing with all these methods is dealing with large state action spaces. It can get computationally expensive, fast.
Yeah, I can imagine. So, how do you handle that?
Function approximation. Representing the value function with something more compact, like a linear combination of features, or even a neural network.
Oh, right. Like in deep Q-learning. That's where things get really interesting.
Absolutely. And then there's direct policy search. Instead of messing with value functions, you just try to find the best policy directly. It's a whole different approach.
So, we were talking about all these different approaches to reinforcement learning, right? Value function estimation, direct policy search, it's a lot to take in.
It is, yeah. And then you've got model-based methods on top of that. It gets complicated fast.
Okay, so model-based, that's where you learn a model of the environment first, right? Like the transition probabilities and such?
Exactly. Things like Dyna, where you learn a model from experience and use it to, supplement the real transitions.
So you're basically creating a simulated environment to learn from, in addition to the real one?
Right. It can be more computationally intensive, but it can also be really powerful, especially when you don't have a perfect model to begin with.
And sometimes you can even use non-parametric models, right? Just storing transitions and replaying them?
Yeah, that's a cool approach. But then there's the whole other side of things, policy search methods.
Oh, right. Like reinforce and all those gradient-based approaches?
Yeah, those. And the gradient-free methods, like, simulated annealing and evolutionary computation.
So, gradient-based methods, they try to find the optimal policy by tweaking the parameters of some policy function, right?
Exactly. Using gradient ascent, ideally. But since you don't usually have the actual gradient, you have to estimate it.
And that can be noisy, I imagine. Especially in episodic problems with long trajectories.
It can. That's where value function methods can sometimes be more effective.
So, actor-critic methods kind of combine the best of both worlds, right? Value functions and policy search?
Yeah, they've been getting a lot of attention lately. Performing well across a variety of problems.
Okay, so, deep reinforcement learning, that's where you throw neural networks into the mix, right?
Exactly. Like DeepMind's work with Atari games. That really put Deep RL on the map.
It's powerful, but it also has its own set of challenges, right? Like, vulnerability to adversarial attacks.
Yeah, that's a big one. And then there's fuzzy reinforcement learning, which uses fuzzy logic to approximate the value function.
Interesting. So, you can express the rules in a more natural language-like way?
Exactly. And inverse reinforcement learning is another cool area. Where you try to learn the reward function from observed behavior.
So, like, figuring out what someone is trying to achieve, just by watching them?
Precisely. It's got all sorts of applications in, robotics and human-computer interaction.
So, we were discussing all these reinforcement learning approaches, but what if you don't have a reward function to begin with?
Then you get into inverse reinforcement learning, or IRL. It's kind of like working backward, you see the behavior, and you try to figure out what the reward must have been.
So, like, watching an expert play a game and trying to deduce their strategy, essentially?
Yeah, exactly. One popular approach is maximum entropy IRL, or maxent IRL. It tries to find a reward function that explains the observed behavior while maximizing the entropy of the trajectories.
Entropy? So, like, keeping things as uncertain as possible, in a way?
Kind of. It avoids making strong assumptions about the reward function that aren't justified by the data. And then there's random utility IRL, or RURL. It assumes the agent has a deterministic policy, but the observer only sees a partial view.
Oh, interesting. So the randomness comes from our limited perspective, not the agent's actual behavior?
Precisely. Then you've got multi-objective reinforcement learning, where the agent has to juggle multiple, often conflicting goals.
Right, like balancing performance with safety, or something like that?
Exactly. Which brings us to safe reinforcement learning. Super important in real-world applications, right?
Yeah, you don't want your self-driving car learning by crashing into things. So, how do you ensure safety?
Well, one approach is risk-averse reinforcement learning, where you optimize a risk measure like conditional value at risk, or CVR. It helps avoid those really bad outcomes.
Makes sense. But CVAR optimization can be tricky, right? Gradient bias, blindness to success.
Yeah, you have to be careful. Then there's this whole other thing, self-reinforcement learning. No external rewards, just internal feelings driving the learning process.
So, like, a robot learning based on its own internal sense of good and bad, essentially?
Yeah, it's a fascinating idea. Uses a memory matrix and emotions and all sorts of, interesting stuff.
Okay, so we've talked about all these different types of RL. But how do you actually compare different algorithms?
Right, that's a crucial question. You train agents on the same environment, run them on test episodes, and compare their scores. Standard statistical tests, like t-tests, can be used.
But just looking at the total episode return can be misleading, right? You lose information about the individual time steps.
Exactly. So, weighting rewards based on their estimated noise can be more informative and give you more statistical power.
So, we're talking about reinforcement learning, and, all these different approaches. It's a pretty broad field, right?
Yeah, it is. From basic Monte Carlo methods to, cutting-edge deep RL and everything in between. It can be tough to keep track of it all.
Definitely. We've got value function estimation, direct policy search, model-based methods. How do you even choose which one to use?
Well, it depends on the problem, of course. Like, if you have a good model of the environment, dynamic programming can be very effective. But if you don't, then you might want to look at Monte Carlo or temporal difference methods.
Right. And then there's the whole exploration-exploitation dilemma. How much do you explore new actions versus stick with what you know works? That seems pretty fundamental.
Absolutely. And the best approach for exploration often depends on the specific problem. Epsilon greedy is a simple but surprisingly effective method, but there are many others.
Like softmax, or UCB, or...
Yeah, exactly. And then you have to think about how to actually learn from experience. How do you update your estimates of the value function or the policy?
Right. Temporal difference methods seem pretty powerful. They can learn from incomplete episodes, which is a big advantage.
It is. And then there's eligibility traces, which can help speed up learning by propagating rewards back in time.
Oh, right. Like in TD lambda.
Precisely. And then for really large state action spaces, you need function approximation. Representing the value function or policy with something more compact, like a neural network.
Which brings us to deep reinforcement learning. That's where things get really interesting, right? Using deep neural networks to approximate these functions.
Yeah, it's been a game changer. But it also introduces its own set of challenges. Like, training these networks can be tricky, and they can be very sensitive to the choice of hyperparameters.
And then there's the issue of stability. These deep RL algorithms can sometimes be unstable and difficult to debug.
Definitely. But the potential rewards are huge. We're seeing amazing results in areas like game playing, robotics, and even finance.
So, it seems like there's a lot of ongoing research in this area. What are some of the hot topics right now?
Well, safe reinforcement learning is a big one. How do you guarantee that your RL agent won't do anything dangerous, especially in real-world applications?
Right. And then there's multi-objective reinforcement learning, where the agent has to balance multiple, often conflicting goals.
Yeah, that's a tough one. And then there's inverse reinforcement learning, where you try to learn the reward function from observed behavior. That's got all sorts of interesting applications.
Like, understanding human behavior, or building robots that can learn from demonstration.
Exactly. And let's not forget about hierarchical reinforcement learning, where you break down complex tasks into smaller, more manageable subtasks.
Right. That can really help with scalability and generalization.
It can. So, yeah, it's a vibrant field with lots of exciting developments happening all the time. It's definitely a space to watch.
So, we've covered a lot of ground on reinforcement learning. From the basics to some pretty advanced concepts.
Yeah, it's a huge field. Everything from, those early dynamic programming approaches to, like, the latest deep RL stuff. It's a lot.
It is. We talked about model-based RL, right? Where you learn a model of the environment?
Right, like Dyna. You build a model and use it to, kind of simulate experience.
So, you're learning from both real and simulated interactions? That's clever.
It is, yeah. Especially when getting real experience is expensive or difficult, you know?
Makes sense. But what about when you don't have a reward function at all? That seems like a pretty fundamental problem.
Then you get into inverse reinforcement learning, or IRL, right? You try to figure out the reward function from observed behavior.
Oh, right. Like, watching an expert and trying to deduce their goals, essentially?
Exactly. Maxent IRL is a popular approach for that. Maximizing entropy, keeping things uncertain.
So, not overfitting to the observed data, essentially?
Right. And then there's RUIRL, where the randomness comes from our limited perspective, not the agent's behavior.
Oh, interesting. So, like, we only see part of the picture, and that introduces uncertainty?
Precisely. Then there's multi-objective RL, juggling multiple goals, often conflicting ones.
Right, like balancing performance with safety, or...
Exactly. Which brings us to Safe RL. Super important for real-world applications.
Yeah, you don't want your self-driving car learning by crashing into things. So, risk-averse RL is one way to handle that?
Yeah, optimizing a risk measure like CVAR helps avoid those really bad outcomes.
But CVAR has its own challenges, right? Gradient bias and...
Yeah, it's not a silver bullet. Then there's self-reinforcement learning, no external rewards, just internal feelings.
So, the agent defines its own reward, in a way? That's fascinating.
It is. Uses a memory matrix and emotions, all sorts of interesting stuff.
So, we've been diving deep into this reinforcement learning thing, and wow, it's a rabbit hole, huh?
It is, yeah. So many different flavors. It's like a buffet of algorithms.
Right? We talked about model-based RL, where you learn a model of the environment, like Dyna.
Yeah, you build that model and use it to, simulate experience, supplement the real stuff.
Clever. Especially when real-world experience is hard to come by, or, expensive.
Totally. But then, what happens when you don't have a reward function? That's where things get tricky.
That's where inverse reinforcement learning comes in, right? IRL. Figuring out the reward from behavior.
Exactly. Like, watching an expert and trying to figure out what they're trying to achieve. Their secret sauce.
Maxent IRL, right? Maximizing entropy, keeping things uncertain.
Yeah. Not overfitting to the data, essentially. And RUIRL, where the randomness is from our limited view.
Oh, right. We only see part of the picture. It's like, watching a magic trick.
Kind of. Then there's multi-objective RL, juggling all those different goals. Often conflicting ones.
Balancing act, right? Like, performance versus safety, or...
Exactly. Which brings us to Safe RL. Can't forget about that. Super crucial for the real world.
Yeah, you don't want your robot learning to cook by setting the kitchen on fire. Risk-averse RL, right? CVAR?
Yeah, optimizing that risk measure. Helps avoid those catastrophic outcomes. But it has its own quirks, you know?
Right, gradient bias and all that. Then there's self-reinforcement learning. No external rewards. Just internal feelings. The agent defines its own reward, in a way. That's mind-blowing. Like a philosophical robot.
It is, yeah. Memory matrix, emotions. It gets pretty deep. But hey, that's reinforcement learning for you. Always something new to explore. Thanks for tuning in, everyone. It's been a blast.
Absolutely. It's been a pleasure discussing this fascinating field with you. Until next time, this is Daily Podcast signing off. Stay curious, folks.
Bye-bye.